Hello friends, myself Dr. D. Trivedi. I am going to teach you D to A conversions and A to D conversions in 6502, and this is our second lecture related with this. In our first lecture, we have studied a resistive divider network by which we can convert a digital information into analog information. Now, what was the drawback in that system or limitation in that system? In that system, the resistance was used R0. Then we have utilized R1, which is equal to R0 by 2. Then we have utilized R2, which is going to be R0 by 4, and so on. That means each resistance is a half value than its previous resistance. And that means number of values resistance we have to utilize. Moreover, current passing through each branch is going to be different. Current passing from MSB for the 10-bit system is going to be 500 times current compared to the LSB, and that's why that is also disadvantage of resistive divider network. Moreover, precise value of the resistance you require, and precision will cost more. That means the more costing is going to be there for resistive divider network. Both this drawback or limitations can be overcome in second type of a network, which is called a binary ladder network, which will convert a digital information into analog information with only two type of resistors, two values of the resistance, that is R and 2R. So now we are going to learning a binary ladders. The binary ladders is a resistive network whose output voltage is properly weighted sum of the digital inputs. Such a ladder designed for a 4-bit is shown in figure 12.6. It is constructed of resistors that have only two values and thus overcomes one of the objections to the resistive divider previously discussed. That means we don't require a many value of the resistance, but we require only two different value of the resistance, many resistors. Here we are going to discuss a 4-bit this binary ladder network. That means 4 bit digital input signals will be there and one output signals will be there. So here LSB is going to be 2 raised to 0, this is going to be 2 raised to 1, 2 raised to 2 and 2 raised to 3. So these are the 4-bit digital inputs will be there, and this is VA is analog output voltage, which is going to be generated from different combination of digital signals, which is going to be from 0000 to 1111. There are 16 combinations will be there. Corresponding to that, you will have a analog output voltage from 0 to a maximum voltage. The left end of the ladder is terminated in a resistor of 2R, and we shall assume for moment that right end of the ladder the output is open circuited. So you can see here that on the left hand side this resistance from nodal point A, the terminating resistor is going to be 2R, and from every nodal points to the digital inputs the resistance is also 2R is going to be selected from point A to 2 raised to 0, B to 2 raised to 1, C2 towards the 2 raised to 2 and D2 towards the 2 raised to 3. The resistance are 2R. While in this manner A to B, B to C and C to D, the resistance are going to be chosen R only. So there are only two value of the resistance are required. In this R to R ladder network, we can say that. Now, let us now examine the resistive property of the network. We'll study what is the equivalent resistance for each branch from each node, assuming that all the digital inputs are at the grounds. Beginning at the node A, the total resistance looking into the terminating resistance is 2R. The total resistance looking out toward the 2 raised to 0 input is also 2R. These two resistors can be combined to form an equivalent resistor of value R as shown in the figure 12.7. So again we can see that figure. You can see that. Consider that all the digital inputs are at 0, 0, 0, 0. That means all these inputs are connected with the grounds. That means 2 raised to 0 is connected with the ground like this. So with respect to the nodal point A, on a terminating resistor is 2R, and from this to the towards the 2 raised to 0, which is also grounded, the resistance is going to be 2R. So both these resistors are going to be equal and they are parallel with each other. Hence, the equivalent resistance of this is half of this resistance, that is going to be R only. So you can utilize that formula R1 into R2 upon R1 plus R2. So 2R plus 2R, that is going to be 4R, 2R into 2R, that is going to be 4R upon 2R plus 2R, that is going to be 4R. So that will be cancelled out and you will get only value of R resistance. So with respect to A, toward the terminating point, the resistance is going to be R only. So we can redraw this circuit in another circuit and we can show that from A to terminating resistance, the equivalent resistance is going to be R. That is combined with this resistance R, and this side it is going to be 2R will be there. That will be your next figure. So you can see that in figure 12.7, from the nodal point B towards the terminating resistance, this resistance R between B and A plus equivalent resistance was R. So this total resistance, they are in a series, hence it is going to be R plus R, so it is going to be 2R from the point B. This side also it is going to be 2R. Again, this is grounded, so this 2R and this 2R, they are in parallel with respect to the point B and ground. And hence, the equivalent resistance is half of this resistance, so it is again it is going to be R. So with respect to the point C, you can see the figure C, B this one, that with respect to the nodal point C, toward this side, there is a resistance R was there, and from B, equivalent resistance was R, which is shown over here. So with respect to the nodal point C, this resistance are R plus R, that is going to be 2R, and this side also it is going to be 2R toward the 2 raised to 2, and this terminal is grounded. Again, these two resistors are in parallel. So equivalent resistance looking back from nodal point C is going to be R, which is shown in a figure 12.7c. So from the point C to the ground toward the terminating terminal, the equivalent resistance is going to be R plus this resistance is going to be R, and this side again it is going to be 2R. This is the way the circuit is going to be continued. Now moving to the node B, we see that the total resistance looking into the branch toward the node A is 2R, as is the total resistance looking out toward the 2 raised to 1 input. These resistors can be combined to simplify the network as shown in the figure 12.7a. From figure 12.7b, it can be seen that the total resistance looking from the node C down the branch toward the node B or out to the branch toward the 2 raised to 2 input is still 2R. The circuit in figure 12.7b can then be reduced to the equivalent as shown in the figure 12.7c. From these equivalent circuits, it is clear that resistance looking back toward the node C is 2R, as is the resistance looking out toward the 2 raised to 3 input. From the preceding discussion, we can conclude that the total resistance looking from any node back toward the terminating resistance or out toward the digital input is 2R. Both are equal resistance to R. Notice that this is true regardless of whether the digital inputs are at ground or at plus V. Why it is like this? When it is ground, you can say that you have connected a digital signal of 0, and when it is connected with the plus V, you can consider that it is connected with a digital signal of 1. Now, the digital inputs, whatever the voltage source is there, that we are taking the ideal voltage source. And when it is ideal voltage source, its impedance is going to be 0. Its internal resistance is going to be 0. And hence, both the conditions, whether it is connected to the 0 or whether it is connected to the 1, both the conditions, the resistance from any node toward the digital input is going to be 2R only. The justification for this statement is the fact that internal impedance of an ideal voltage source is 0 ohm, and we are assuming that digital inputs are ideal voltage sources. We can use the resistive characteristic of the ladder to determine the output voltage for the various digital inputs. So, if the voltage source is connected to the MSB, that is 2 raised to 3 inputs, then how much it will contribute a analog output voltage, that we have to find out. For that, let us take a digital input of 1000. That means on MSB, that is at 2 raised to 3, the plus V is connected, and 2 raised to 2, 2 raised to 1, 2 raised to 0 inputs, they are grounded because they are connected with the 000. So, we can use the resistance characteristic of the ladder to determine the output voltage for the various digital inputs. First, assume that the digital input signal is 1000. With this input signal, the binary ladder can be drawn as shown in the figure 12.8a. Like this. You can see that this is the binary ladder network. This is the MSB where 1 is there. That means the digital voltage source of plus V is connected over here. The rest of the inputs are 000, so they are grounded. Now, with respect to the nodal point C, toward this side, the equivalent resistance is going to be R. And again from C to D, the resistance is going to be R. So, R plus R is going to be 2R. That means with respect to the nodal point D, terminating resistance is going to be 2R, and toward the digital input, the resistance is also going to be 2R. And here there is a one signal, digital signal 1 or plus V voltage is given. So, with respect to plus V1 and ground, there are two resistance 2R and 2R. Both are the same resistance, and using the voltage divider, using a voltage divider circuit, you can see that voltage between D and grounds is equal to V divided by total resistance 2R plus 2R into the voltage across the resistance, that is going to be 2R. So, V upon 4R into 2R, that means the voltage at the output VA is going to be plus V by 2. Since there are no voltage source to the left of the node D, the entire network to the left of this node can be replaced by a resistance of 2R to form equivalent circuit shown in a figure 12.8b. From this equivalent circuit, it can be easily seen that the output voltage is VA is equal to IR. I is equal to voltage upon total resistance, that is equal to V upon 2R plus 2R into R is equal to 2R, and hence it comes out to be plus V by 2. Thus, a 1 in the MSB position will produce an output voltage of plus V by 2.
to determine the output voltage due to the second MSB. Let us assume a digital input signal of 0100 is given. This can be represented by circuit shown in figure 12.9a. Since there are no voltage source to the left of the node C, the entire network to the left of the node C can be replaced by the resistance of 2R as shown in a figure 12.9b. So you can see that it is connected like this. MSB is going to be 0 volt, so it is grounded. This is second MSB is going to be 1. That means it is connected with the power supply plus V volt. Then here also it is going to be grounded. This is also grounded because this is going to be 0 0 0 1 0 0. This way the digital input signal is given. Now from the nodal point C, this side, the equivalent resistance from the B onwards is going to be R only. So R plus R is going to be 2R. That means from the C toward the terminating resistance, the equivalent resistance is going to be 2R. And toward this side, it is also going to be 2R. That means this network A can be reduced to the network B. From the C toward the terminating resistance is going to be 2R, and toward the digital input also it is going to be 2R. This we can consider a voltage divider circuit, and here the equivalent resistance is going to be R. By considering this V is going to be connected to the ground. So using the Thevenin's theorem, we can say that voltage across C and ground is going to be V by 2, and that means the voltage source is going to be V by 2, and Thevenin's equivalent resistance is going to be R. That is going to be equivalent resistance of these two which are connected in parallel. Hence, this circuit B can be reduced to the circuit C, where the voltage source, Thevenin's voltage, is going to be plus V by 2 with the series Thevenin's resistance of R. This is a misprint. Here cannot be a 2R. It is only R. So this R plus this R is going to be 2R. And that means this terminal is connected to the grounds. So again you can redraw this circuit like this one. The voltage source is going to be V by 2, and this is going to be R plus R. That means total resistance is going to be 2R between this source and point D. And from point D to the grounds, again it is going to be 2R. So you can say that plus V by 2 divided by R plus 2R. That is going to be current, multiply by 2R. That is the resistance. That comes out to be V by 4. So the one in the second MSB will contribute a output voltage of V by 4. Similarly, if we give one signal over here and all other is going to be grounded, this is going to be 0, this is going to be 0, this is going to be 0. That means at 2 raised to 1 position, there is one signal is going to be there, plus V volt is there, that will contribute a output voltage is going to be V by 8. Similarly, from here 1 is going to be there, then it will contribute a output voltage of V by 16. And if it is more number of bits are going to be there, then V by 32, V by 64, and like that way. Let us now replace the network to the left of the node C, which is Thevenin's equivalent, by cutting the circuit on the jagged line shown in a figure 12.9b. The Thevenin's equivalent is clearly a resistance R in series with the voltage source of plus V by 2. The final equivalent circuit with the Thevenin's equivalent includes is shown in a figure 12.9c. From this circuit, the output voltage is clearly VA is equal to plus V by 2 divided by the resistance, that is going to be I, current, R plus 2R into the resistance, that is going to be 2R, that comes out to be plus V by 4. Thus, the second MSB provide an output voltage of plus V by 4. This process can be continued, and it can be shown that the third MSB provides the output voltage of plus V by 8. The fourth MSB, that is LSB, will provide the output voltage of plus V by 16, and so on. The output voltage for the binary ladder are summarized in figure 12.10. Notice that each digital input is transformed into properly weighted binary output voltage, which can be understood very well from this example, as well as the table is given here. Binary ladder output voltage for MSB. Binary weight of the MSB is going to be 1 by 2, and output voltage is going to be multiplied by V. So it is going to be V by 2. Second MSB, binary weight is going to be 1 by 4, and its output voltage contribution is going to be V by 4. Third MSB, binary weight is going to be 1 by 8, that is 1 upon 2 raised to 3, and output voltage is going to be V by 8. Fourth MSB, output voltage is going to be 1 upon 16, that is 1 upon 2 raised to 4, and output voltage is going to be V by 16, and so on up to the nth MSB or LSB. Binary weight is going to be 1 upon 2 raised to n, and output voltage contributed by the LSB is going to be V upon 2 raised to n. So this can be utilized for this example. What are the output voltages caused by each bit in a 5-bit ladder network? If input levels are binary 0 corresponds to 0 volt and binary 1 corresponds to plus 10 volt. Solutions. The output voltage can easily be calculated using figure 12.10. They are: the first MSB will contribute that VA is equal to V by 2, and V is equal to 10 volt. So 10 volt divided by 2, that is equal to 5 volt. So if one signal at MSB is there, that will contribute a plus 5 volt. Similarly, second MSB, that is contributing voltage, is going to be V by 4, that is equal to plus 10 by 4, that is equal to plus 2.5 volt. The third MSB, that will contribute VA is equal to V by 8, that is equal to plus 10 upon 8, that is equal to plus 1.25 volt. Fourth MSB, that is going to be contributing V by 16, that is equal to 10 upon 16, that is equal to plus 0.625 volt. And fifth MSB or LSB, which will contribute VA is equal to V upon 32 is equal to plus 10 upon 32, that is equal to plus 0.3125 volt. So this way, because it is a 5-bit system, we have calculated up to the 5 to 1 upon 2 raised to 5, like that way. It can be increased or decreased depending upon number of bits. Since this ladder is composed of linear resistors, it is a linear network, and the principle of superposition can be used. This means that total output voltage due to the combination of the input digital levels can be found to be by simply taking the summation of the output levels caused by each digital input individually. So this is the resistive network, and it is a linear network. So one at each input will contribute its own at the output, and that can be taken summation to get the proper output or actual output depending upon the digital signals, which we'll see in the next example. In equation form, this output voltage is given by VA is equal to V by 2, that is contributed by MSB, plus V by 4, which is contributed by the second MSB, plus V by 8 contributed by the third MSB, plus V by 16 contributed by the fourth MSB, etc., plus V by 2 raised to n, which is going to be contributed by LSB or nth LSB, MSB, where n is the total number of bits in the input. This equation can be simplified somewhat by factoring and collecting the terms. The output voltage can then be given in the form VA is equal to. So this equation can be reduced into this form by taking a factoring and collecting certain terms. So this equation VA is equal to, that means analog output voltage corresponding to the digital signals is going to be given by this equation 12.3, which is nothing but V0 into 2 raised to 0 plus V1 into 2 raised to 1 plus V2 into 2 raised to 2 plus V3 into 2 raised to 3 plus etc. plus Vn minus 1 2 raised to n minus 1 upon, that is denominator, 2 raised to n, where V0, V1, V2, V3 etc. Vn minus 1 are the digital input voltage levels. That means V0 can be 0 also, or it is going to be V volt also. Similarly, V1, if it is corresponds to the binary 0, then it is going to be 0 volt. If it corresponds to 1, then V1 can be plus 10 volt, or whatever that plus V volt is going to be given. So this equation 12.3 can be used to find out the output voltage from a ladder network for a digital input signals, which we can see in this example. Find the output voltage from a 5-bit ladder that has a digital input of 11010. So this is a 5-bit network. Assume that 0 corresponds to 0 volt and binary 1 corresponds to plus 10 volt. Let us find out using this formula. V0 into 2 raised to 0 plus V1 into 2 raised to 1 plus V2 into 2 raised to 2 plus V3 into 2 raised to 3 plus V4 into 2 raised to 4, because it is a 5-bit system. See this digital input number. This is LSB 0. So V0 is equal to 0. V1 is equal to 10 volt. V2 is going to be 0 volt. V3 is going to be 10 volt. And V4 is going to be 10 volt. That we can substitute here. So V0 is going to be 0 into 2 raised to 0 plus 10 into 2 raised to 1 plus 0 into 2 raised to 2 plus 10 into 2 raised to 3 plus 10 into 2 raised to 4. Now, wherever it is going to be multiplied with the 0, that can be removed. Remaining things, 10 is going to be taken as output because that 10 is going to be common everywhere. So it is taken outside. Remaining is the position weight. So 2 raised to 1 is going to be 2, 2 raised to 3 is going to be 8, and 2 raised to 4 is going to be 16. So 16 plus 8, 24 plus 2, 26, multiply by 10, so 260 divided by 32, 2 raised to 5 is going to be 32. That comes out to be plus 8.125. So this plus 8.125 volt is an analog output voltage corresponding to the digital input signal 11010 in the system. These solutions can be checked out by adding the individual bits contributing, calculating in the example. That means how much this will contribute? This is going to be contributing V by 2, the first one. That means 10 by 2 is going to be 5 volt. Second MSB will contribute V by 4. That is going to be 2.5 volt. Third MSB is going to be 0, so it is not going to be contribute anything. Fourth MSB will contribute V by 16, and that we can add and we'll find out that it is going to be same as this one, getting from this formula, that is equal to plus 8.125 volt. Notice that equation 12.3 is very similar to the equation 12.1, which was developed for the resistive divider network. They are in fact identical with the exception of the denominators. This is subtle but very important difference. Recall that full scale voltage for the resistive divider network is equal to voltage level of the digital input one. So you can see the difference between the two type of the network. Resistive divider network, when all the digital inputs are going to be 111, that is full scale. then the total voltage contributed by each bit, and if you take the summation of that, then you will find out that it comes out to be equal to this 1, or it is equal to the same as digital input level 1. But in case of the binary ladder network, denominators are different. In a previous case, that is a resistive divider network, denominator is 2 raised to n minus 1, and in this case it is 2 raised to n. That means here the voltage is going to be slightly less than the previous case. So when all the digital inputs are going to be high, or it is going to be 1-1 conditions, then output voltage is not going to be equal to digital input 1, but it is slightly less than digital voltage levels. On the other hand, examination of the equation 12.2 reveals that the full scale voltages for the ladder is given by Va is equal to V by 2 plus V by 4 plus V by 8 plus V by 16 plus etc. V upon 2 raised to n. The terms inside the bracket form a geometric series whose sum approaches 1, gives a sufficient number of terms. However, it never quite reaches to the 1. That means it cannot be a total voltage is equal to the voltage level provided at digital input, but it is slightly less. Therefore, the full scale output voltage of the ladder approaches V in the limit, but never quite reaches to V, which we can see in this example. What is the full scale output voltage of a 5-bit ladder in the example 12.4? The full scale voltage is simply the sum of the individual bit voltage contributed. MSB will contribute V by 2, that is going to be 5 volt. Second MSB will contribute V by 4, that is going to be 2.5 volt. Third MSB will contribute V by 8, that is going to be 1.25 volt. Fourth MSB will contribute V by 16, that is equal to 0.625, and fifth MSB or LSB will contribute V by 32, that is equal to 0.3125, and summation of this will get that is equal to plus 9.6875 volt. This is slightly less than the V is equal to 10 volt, which is applied for binary 1. So you can say that it never equals to the V volt, but it is slightly less than V volt applied for the digital input. To keep the ladder in a perfect balance and to maintain the symmetry, the output of the ladder should be terminated in a resistance of 2R. So until now we have considered that Va on the right hand side was open circuited, but when it is open circuited, the ladder is not in a perfectly balanced circuit. So to maintain at a perfect balanced circuit, this Va should be terminated with the load resistance of 2R. So it will provide a perfect balance to the ladder network, as well as it will maintain the symmetry for the output of the ladder. This will result in a lowering the output voltage, but if the 2R load is maintained constant, the output voltage will still be properly weighted sum of the binary input bits. So if this load resistance 2R is maintained constant, then the circuit will be in perfectly balanced, and input resistance seen by each digital input is going to be constant, and hence it is output voltage contributed by each digit is properly weighted sum will be there. If the load is varied, the output voltage will not be properly weighted sum, and care must be exercised to ensure that load resistance remains constant. Terminating the output of the ladder with a load of 2R also ensure that the input resistance to the ladder seen by each of the digital voltage source is a constant. With the ladder balance in this manner, the resistance looking into any branch from any node has a value of 2R. Thus, the input resistance seen by any input digital source is going to be 3R. This is the definite advantage over the resistive divider network. Since the digital voltage source can now be designed for the same load, like this, we can see in the example this one. Suppose that the value of R for a 5-bit ladder described in example 12.3 is 1000 ohms. So all the R is equal to 1000 ohms and 2R means 2000 ohms. Determine the current that each input digital voltage source must be capable of supplying. Also determine the full scale output voltage, assuming that the ladder is terminating with the load resistance of 2R, that is going to be 2000 ohms. So, your ladder network is terminating with the 2R. So, here there are 2R resistance is connected as a load. The input resistance into the ladder seen by each of the digital source is going to be 3R, because equivalent resistance from the D point is going to be R only. Toward the MSB, it is the resistance is going to be 2R, and toward the terminating resistance also it is going to be 2R, and hence the equivalent resistance, Thevenin's equivalent voltage is going to be 10 volt, and you can say that the equivalent resistance is going to be R only. And hence you can say that that circuit can be replaced by ladder Thevenin's equivalent, which is having a voltage source of when all the inputs are going to be high, that is considered to be 9.6875 volt, and with a series resistance of R, that is going to be Thevenin's equivalent resistance will be there. So this voltage source is seeing a total resistance of R plus 2R, that is going to be 3R resistance it is seen. So what will be the current? Voltage divided by the total resistance. So voltage divided by R plus 2R, 3R, and R is equal to 1000. So 3000. So normally we can say that I is equal to 10 upon 3 into 10 raised to 3, that is equal to 3 into 1 upon 3 milliampere current without 2R load resistors. The resistance looking into the MSB terminal is actually 4R, because 2R towards the MSB and 2R towards the terminating resistance. So the total resistance is going to be 4R seen by the voltage source. But with this load, the resistance is going to be 3R only. The no load output voltage of the ladder has already been determined in the example 12.5. This open circuit output voltage along with the open circuit output resistance can be used to form a Thevenin's equivalent circuit for the output of the ladder. The resistance looking back into ladder is clearly R, that is equal to 1000 ohms. Thus, the Thevenin's equivalent is as shown in the figure 12.11. From this figure, the output voltage is, that is voltage across this resistance 2R, that is equal to current multiplied by this resistance 2R. What will be the current? Voltage divided by the total resistance. Voltage is going to be plus 9.6875 divided by the resistance, that is going to be 2R plus R, that is going to be 3R, multiplied by this resistance 2R. That comes out to be plus 6.4583 volt. Now you can see that the voltage has lowered compared to the previous case. Open circuit, when all the digital inputs were high, then the output voltage was 9.6875, slightly less than 10 volt. But now, with the load resistance of 2R, the circuit will have perfect balance and it will maintain a symmetry, and output voltage is perfectly weighted sum of corresponding input digital signals. But that voltage comes out to be 6.4583. It is lowering. The operational amplifier shown in figure 12.10a is connected as a unity gain non-inverting amplifier. So, output of this ladder network or resistive divider network can be connected to the operational amplifier, which can act like a unity gain non-inverting amplifier. What is the meaning of unity gain? Gain is equal to output voltage upon input voltage. So if the output voltage upon input voltage is going to be same or it is equal to 1, then we can say that the gain of this amplifier is 1 or unity, and hence it is called unity gain amplifier and non-inverting amplifier. So output is same signal as input, that means the output is positive as the input is positive, or it is negative if it is input is negative. That means input is not inverted. It has very high input impedance and output voltage is equal to the input voltage. Hence, it is thus good buffer amplifier for connections to the output of a resistor ladder. It will not load down the ladder and thus will not disturb the ladder output voltage. So, this is utilized as a buffer amplifier. Input impedance of the op amp is very high, is infinity. So it will not load down the ladder network or resistive divider network. That is the main purpose. Its gain is going to be 1 only. There are two ways it can be connected. It can be connected as a voltage to the voltage amplifier, non-inverting amplifier, or it can be connected to voltage to the current amplifier. We'll see both the things here. VA will be then appear at the output of operational amplifier. This is the circuit A and this is going to be the circuit B. You can see that. Here, this output voltage of ladder network is analog output voltage, which is considered to be input voltage for this op amp, connected to the non-inverting terminal of this one, and it is having a unity gain. So output voltage is equal to input voltage. It is in the same phase, and this non-inverting terminal is connected to the output. That means it will provide a feedback resistance of 0, and hence it is a voltage to voltage amplifier with unity gain and non-inverting amplifier. While this one, you can see that the output of the ladder network is connected to the inverting terminal of the op amp. Moreover, there is a feedback resistance R is connected here. So this is a current to the voltage amplifier. So input of this one is going to be the current. This will act as a virtual ground, and here the voltage is going to be 0 volt. So each branch is providing the current I1, I2, I3, etc., depending upon their position weight. And that current is coming toward the node this, that is summation of the input currents, and that is equal to the currents going out of this node, that is going to be the total current I, which is equal to I1 plus I2, etc., and that current is passing through this feedback resistance R. So the output voltage VA is equal to minus I into R. Minus sign because the direction of the current and the signal is going to be inverted. So this way we can obtain current to voltage amplifier here. Connecting the operational amplifier with the feedback resistance R as shown in the figure 12.12b result in an amplifier that act as a inverting current to voltage amplifier. That is, the output voltage VA is equal to the negative of the input current I multiplied by R. The input impedance to this amplifier is essentially 0 ohms. Thus, when it is connected to the R to R ladder network, the connecting point, that is work as a virtual ground or virtually at a ground potential, 0 potential. In these configurations, the R2R ladder will produce a current output I, that is binary weighted sum of the input digital signals or levels. For instance, the MSB produce a current of I1 is equal to V upon 2R. The second MSB will produce a current of I2 that is equal to V upon 4R, and so on. But the operational amplifier multiplied these currents by minus R, and thus VA output voltage is equal to minus R into the currents I1 plus I2 plus I3 plus I4 etc. IN. Summation of the currents, that is equal to VA is equal to minus V by 2, minus V by 4, minus V by 8, minus V by 16 etc. minus V upon 2 raised to n. This is exactly the same expression given in the equation 12.2 and 12.3, except for the sign. Thus, D to A converter in figure 12.12a and b will provide the same output voltage VA except for the sign. In figure 12.12a, the R2R ladder and operational amplifier are said to operate in a voltage mode, while the connection in figure 12.12b is said to be operate in a current mode. Now, there are certain small questions related with this binary ladder network. What is the LSB weight of 6-bit resistive network? The binary weight of the LSB is equal to 1 upon 2 raised to n, because n is the number of digital inputs. In case of resistive divider network, the weight of LSB is equal to 1 upon 2 raised to n minus 1. Here it is 1 upon 2 raised to n. What is the value of VA in example 12.2 if the MSB is going to be 0? What is the value of VA in example if the MSB is going to be 0? I don't remember example 2, but except this one V by 2, all other voltage will be there. If the ladder in example 12.4 is increased to the 6th bit, but what is the output voltage due to the 6th bit alone? That means due to the MSB alone. So, output voltage, if you consider through the MSB, then it is going to be V by 2. And if you consider that output due to the 6th bit, which may be LSB on other sides, then it is 1 upon 2 raised to n or V upon 2 raised to n. So, 10 upon 2 raised to 6 will be there. So, 10 upon 64, that will be the output. And fourth one, if the ladder in example 12.4 is increased to the 6 bits, what is the full scale output voltage? You have to take the addition of this one, V by 2 plus V by 4 plus V by 8 plus V by 16 plus V by 32 plus V by 64, and that you can take the addition and you can find out this voltage. Thank you very much, friends.